The last few videos in this series have focused on the Schwarzschild black hole and looked at a number of ways of measuring the space-time around it. However, we now want to try to move closer to an understanding of Einstein's field equations. In particular, for this video, we want to think about what these two things are. The first is the Ricci Curvature Tensor, and the second is called the Curvature Scalar, or sometimes the Ricci Scalar. Each of them can be considered to measure some aspect of the curvature of an event in space-time, and in order for us to understand why that's so, we need to discuss a third tensor which is not in Einstein's field equations, called the Riemann Curvature Tensor. And even though we've talked a lot about a number of curved spaces in previous videos, we've never really discussed what we actually mean by a measurement of curvature. How can we put a number or numbers to it? In particular, if the space or even the space-time has a curvature which varies with position, and curvilinear coordinates are therefore used, then we need a way to describe the curvature at every point in the space, or rather every event in the space-time. In this video, therefore, we will discuss, as best we can, without some heavy mathematics, these three main measures of curvature, which will be useful when we come to think about Einstein's field equations. Here's a quick overview of the direction in which we'll be going in the rest of this video. The first measure of curvature that we'll discuss will be the Riemann Curvature Tensor. This is a tensor with 4 indices, 1 upper or contravariant and 3 lower or covariant, and when discussing some space or other it's written like this, R, R, S, M, N. And when discussing space-time, like this, with Greek letters for the indices, r, rho, sigma, mu, nu. And having 4 indices means that for a two-dimensional space, this Riemann curvature tensor will have 2 times 2 times 2 times 2, 16 different numbers at each point in the space, which will describe the curving of the space at that point. Of course, if we were considering 4-dimensional space-time, it would have 4 times 4 times 4 times 4, 256 numbers at each point or at each event in the space-time. Get ready for some big sets of numbers, but hopefully we can keep the mathematics simple by cutting a few corners. Don't worry at this stage as to why the indices are both upper and lower. You'll see where they come from when we discuss it in a moment. You might want to be reminded, however, that this upper and lower index business relates, amongst other things, to the 2 distinct ways in which the values of the measured components of a tensor transform when moving from one frame of reference to another. We had, in video number 8, transformation formula like these for changing the measurements of the components which had been made using the red frame of reference into the measurements you would get by using the blue frame. This equation is for the contravariant components, and this for the covariant. In what we shall do later when we come to discuss Einstein's field equations, we won't actually need either of these equations, but what we will need is another important fact about indices, namely that an index can be changed from upper to lower, or the other way around, by using the metric tensor. For example, if we had this representing the contravariant components of a tensor, actually this is a vector here as it only has 1 index, we could convert it so that it had a lower index by multiplying by a form of the metric tensor like this, Tm equals Gmn times Tn upper, and then doing the appropriate sum over n. In a similar way, of course, we could convert the lower to an upper like this. Just as a reminder, in 2 dimensions, this last equation, after summing, would give us these 2 equations for the new components T1 and T2. The new upper component contains all the old lower components, each multiplied by some component of the metric tensor. And this use of the metric tensor to change from lower to upper or vice versa is one kind of manipulation that we will need at some point in our later discussion. Okay, that's a very short introduction to the Riemann curvature tensor, which we'll discuss in more detail in a moment, r rho sigma mu nu. Now from that tensor, we will then extract a subset of its components, those numbers at each point or event in space-time, to make a much simpler looking tensor called the Ricci Curvature Tensor. This will only have two lower or covariant indices and would be written like this for space, RSM, or when discussing space-time, like this, R sigma mu. This Ricci tensor will be a useful but different measure of the curving of space or space-time at a particular place or event. Clearly, having only two indices means that for a two-dimensional space, this Ricci tensor will have only 2 times 2 or 4 different numbers at each point in the space to describe the curvature at that point. Of course, if we were dealing with 4-dimensional space-time, there would be 4 times 4, 16 numbers, just as there are for the metric tensor, which we often write as g mu nu. In that sense, the Ricci tensor kind of matches the metric tensor, and so is likely to be more useful in Einstein's field equations. Finally, the third thing that we'll discuss in a moment, which can be used to describe the curvature at a point or event, is what is sometimes called the curvature scalar. Once again, this will entail taking a subset, this time, of the components of the Ricci tensor, and will produce just a single number at each point in space or event in space-time. This curvature scalar will be written like this, R. It has no indices and could be said to be a tensor of 0 rank. It means at each point or event there will be only one number, which will somehow be a measure of the curvature at that point. Clearly, like the others, this R can vary from place to place or from event to event, but only one value is involved at each of them. So this is where we're going in the following. We'll start with the big one, the Riemann Tensor, and hopefully show more or less what that means. Then we'll see how part of that is used to make the Ricci tensor, and then again finally how part of that is used to make the curvature scalar. However, in order to start talking about the first of these, the Riemann Curvature Tensor, we need first to consider the concept of what is called parallel transport. This should make the idea of curvature come out fairly naturally. Let's go back to thinking just about space, not space-time, and consider this flat two-dimensional plane, which I've again put boundaries on for convenience. It's not curved in any way. Let's imagine having a vector v in it at some point, say here at the red dot. This vector could be the velocity of a particle in the space, or a value of the field there, or whatever. And remember that it's at the point, at the red dot, even though we've drawn it with an extended green arrow to illustrate its size and direction. Then, without thinking about any time coordinates, we could imagine parallel transporting this vector around a loop of some sort in this flat space and bringing it back to its original position, the red dot. It could be any shaped loop, a circle, a square, a triangle, or whatever, but let's take a triangle shown here with blue dotted lines, as this will fit in with another illustration in a moment. As the vector is moved around the loop, we make sure that its direction doesn't change. From point to infinitesimally close point, the vector is kept pointing in exactly the same direction. Don't think about how you would do that or why you'd want to do it, but rather if you did it, it should be fairly obvious that if the space is flat, then the vector would come back to its original position with exactly the same size and direction with which it started. The imaginary movement of a vector in that way is called parallel transport. You've kept the direction of the vector the same, parallel to itself as it edges along, but you've moved it around the loop, and coming back to the same place in a flat space means the vector will be unchanged. Now, here's where that idea is helpful in defining what we mean by not just curvature, but the curvature at a point. We'll now imagine exactly the same thing, but this time we'll do it with a vector in a curved space. And as an example, we'll take the two-dimensional surface of a sphere. And we'll take the same vector v, say, here, on what we might call the equator of this sphere. Now this vector may look angled, but it's pointing what we might call north. And it looks angled because the sphere is tilted towards us. You can see the North Pole. Also remember that although the green arrow looks as though it's pointing out of the plane away from the sphere, this vector v is at the point on the surface and is pointing along what seems to it to be an infinitesimally small flat surface, the tangent plane at the red dot. We'll now consider this triangle on the surface, shown by the blue dotted lines, which take up a quarter of the upper hemisphere, and we'll imagine that the vector is parallel transported around the triangle, all the time keeping it pointing in the same direction as it inches along from point to infinitesimally close point around this loop. Upon return to the starting position, it should be obvious that the vector, which was kept parallel to its original direction at all times, ends up having been rotated by what looks here to be 90 degrees. This is because of the curvature of this two-dimensional surface. It turns out, however, that the angle by which the vector rotates doesn't just depend on the curvature, but also on the area of the loop that it was taken around. And you can perhaps appreciate that if you consider doing the same exercise but around a bigger loop, say half the upper hemisphere. You can see that after parallel transporting the vector around this loop, the angle that it's been rotated by is 180 degrees, twice that of before. The curvature is the same, but of course the area of the loop is twice as big. For double the area of the loop, you get twice the rotation of the vector. And this concept that parallel transport of a vector in a curved space produces a rotation proportional to the area of the loop gives us a way of describing the curvature at a point in the space. If we were to divide the rotation of the vector by the area that it went around, and then let the area, the loop, get smaller and smaller, tending to zero, we will get a calculus-type measurement of the curvature at the point in the space, the rotation per unit area. And this whole idea and this kind of result will lead us to the Riemann Curvature Tensor. However, as you'll see in a moment, we won't focus on the rotation of the vector, but rather we'll consider the change in the components of the vector as it's taken around the loop. This will essentially end up giving us the Riemann Curvature Tensor. As mentioned, we will then be able to get the other measures of curvature from it, and those will become part of Einstein's field equations. So let's dig into the idea of the Riemann Curvature Tensor, the granddaddy of them all. Although we'll move to thinking about four-dimensional space-time in a few minutes, consider for simplicity a two-dimensional space of x1 and x2, or x and y, and assume that the space is curved in some way. It's illustrated here using perspective to embed the surface within a third dimension, but the curvilinear coordinate system of x1 and x2 has not been shown. Let's now imagine a vector v at some point in this space, here, at this red dot. Again, it could be the velocity of a particle at the point, or the value of a field in that region. As mentioned previously, we illustrate it as an extended green arrow, though it really only exists at the red dot. We'll assume that it has contravariant or upper components v1 and v2 in this x1, x2 frame of reference, although as mentioned at this stage no coordinate directions for x1 and x2, and therefore e1 and e2, have yet been shown on the diagram. However, if those components v1 and v2 are contravariant, we can say that the vector would be given by v1 e1 plus v2 e2. Now, imagine parallel transporting this vector around an infinitesimally small loop dx1, dx2 from that point and back again. You can now see the directions here of the coordinate lines x1 and x2 at the red dot, and this time we're taking the loop as a rectangle rather than a triangle. Once that transport loop is done, we will assume that because the two-dimensional space is curved, then the vector will end up being slightly different, say like this, and we'll label it v dashed. Next, rather than using the angle of rotation as the measurement of the change of the vector, the change can be illustrated by the vector difference between v dashed and v. We show it here in brown as a small vector dv. This obviously also exists at the red dot, but it helps us to visualize it more clearly by drawing this extended diagram. Let's now copy the dotted lines of dx1 and dx2 up here as guides, still remembering it's really at the red dot. And then we'll illustrate the two contravariant components of dv, which we'll call dv1 and dv2. Now remember, from what we've discussed in the past, these, which I'm writing in italics, are not actually the component vectors which make up dv, even though for convenience I've shown the parallelogram as though they are. dv1 and dv2 in italics here are strictly speaking the contravariant components, which along with the basis vectors would make up those component vectors like this. dv1 as a vector would be dv1 component times the basis vector e1 and so on. We had a discussion about this kind of thing in an earlier video. The drawing shows vectors, but the labeling is really for the component values. Anyway, it should be clear that dv1 and dv2 in the diagram are scalars, describing the measured changes of the vector v in the x1 and x2 directions at the point at the red dot. We know that these two components come about because of the curvature of the two-dimensional space at the point, so their values obviously are to do with the metric tensor at that point. However, it should also be clear that their values will also be proportional to the area dx1 times dx2, and if you think about it, to some linear combination of the original components of v, v1 and v2. We can show that side of things using these two equations, where a, b, c and d are constants. Each of these equations shows a kind of multilinear relationship. What the first of them is saying is that the change dv1 in the v1 component of the original vector must not only depend on the area of the loop, but also on each of the original components of the vector v1 and v2. That dependency will be linear or multilinear, and the linearity will be shown in what we might call the gradients a and b. The same of course goes for the second equation for the change dv2 in the v2 component of the vector v, where the multilinearity will come out in the constants c and d. All four of these constants, a, b, c and d, must come from the curvature of the space, or rather the curvature of the coordinate system which is measuring the space, and so they will in turn depend on the metric tensor at that point. Now at this stage we could imagine dividing both these equations by dx1 dx2 and letting that small area tend to 0, which would mean that these expressions would be some kind of measure of the instantaneous changes in the contravariant components of the vector v at that point. We won't actually do that division or go to the calculus limits, but we'll rather leave the equations as they are as we continue to work through things, all the time realizing that ultimately we will be working in that limit. Clearly a, b, c and d are the important things that determine the curvature of the space at that point. v1 and v2 are all to do with the actual vector v, and it's a, b, c and d that are to do with the curvature at the point. Now, it's extremely important that you're reasonably comfortable with these two equations. Even though we've not said what the constants a, b, c and d are, the form of the equation should make sense. For example, the change dv1 must not only depend on the area of the loop dx1, dx2, but must also depend on the size of the original vector v, or rather its two components at the point v1 and v2. It must also, of course, depend on the constants a and b, which in turn must come from the metric tensor. Anyway, think about it. You have to be happy with the basic mathematics here, because these two equations are at the heart of what follows. These two formulae, even without knowing what A, B, C and D are, should make sense in principle. In other words, in terms of what the two components dv1 and dv2 of the change in the vector will depend on. The mathematics which follows may get a bit lengthy, but it's fairly basic mathematics. There's just quite a lot of it. These two formulae, which stem from parallel transport around a loop, will be the foundation of what follows as we move through some awkward mathematical manipulations towards thinking about the Riemann Curvature Tensor, and then later both the Ricci Tensor and the Curvature Scalar. Okay, so the next thing to stress is that it should be obvious that in some way or other the four constants a, b, c and d must have something to do with the metric tensor at the particular point in the space, and that it really ought to be possible to calculate these four constants from the metric tensor at that point in the space. Also, as we're dealing in this case with two dimensions, we can say that at the position of the red dot there will be four values within the metric tensor, four values at that point. However, we can't assume that these g values are constant over the space, and so we could also think of there being values of the gradients of these g values at each point in the space as well. Gradients with respect to x1 and also gradients with respect to x2. So that gives us possibly 12 numbers at each point in the space at the red dot, all of which may contribute to how the vector gets changed as it goes around the infinitesimally small loop. 12 things that could affect the values of dv1 and dv2, and hence be a part of A, B, C and D, even just for two dimensions. And then, of course, what about the second derivatives with respect to x1 and x2, a kind of accelerating change in the g value from one point to another? I won't write them out, but that makes many more numbers at each point in the space which just might need to be taken into account in calculating the values of A, B, C and D in these two dimensions. Well, if you want to look into the actual mathematical calculations for those four constants A, B, C and D, then feel free. But here are the results. Each one is a mixture of the derivatives of the Christoffel symbols and the products of Christoffel symbols. Notice that in these expressions I've coloured the indices. I've put the 1 and 2 of the loop dimension, x1 and x2, in red, and all the other indices in blue, except for the summation index I, which I've left black. Those black indices will mean that instead of two terms here, we will actually have four, and that's just for two dimensions. Notice that although these expressions for the constants look pretty horrific, it's actually even worse because they contain Christoffel symbols, which are themselves a kind of shorthand for bits of the metric tensor and derivatives of the metric tensor. What a mess. Perhaps the best thing to do is to try and take an overview of what we've got here. It's clear that the coefficients A, B, C and D for two dimensions depend not only on the metric tensor values themselves, but also on their differentials as contained in the Christoffel symbols. On top of that, the four coefficients contain differentials of the Christoffel symbols, and so there is a second order rate of change involved as well. And they also contain products of the Christoffel symbols, and that will give squares and cross terms of the metric tensor and of its derivatives. Now, before we try to simplify this or bring it all together in some way, there's one more thing to note. This is all only for a two-dimensional curved space. How can we possibly shift from this to a four-dimensional space-time? At first sight, you might start to think that we will need to take a vector around some kind of four-dimensional loop in the space-time. But in fact, we don't. We will always deal with 2 dimensions, but we'll do it multiple times using multiple planes within 4-dimensional space-time. And that's how we will upscale from these 2 dimensions to the Riemann Curvature Tensor for 4-dimensional space-time. Assuming therefore that the principles of what we've just done are fairly clear, let's try to hold on to the simplicity of the basic equations for dv1 and dv2 and accept the expressions for the values of a, b, c and d, and then build from there. So, sticking with these 2 dimensions for the moment, x1 and x2, first of all focus on the expression for the constant a. Ignoring the I summation in black, which in 2 dimensions will just give these extra terms, we can say that in very simple terms this whole thing can be thought of as some kind of tensor-looking component which has one upper blue index, one lower blue index and 2 lower red indices. And those red ones come from the dx1, dx2 loop. We could therefore reorder the lower numbers and rewrite the coefficients a as r1, 1, 1, 2 like this. One upper or contravariant index and one lower covariance index in blue, both of which came from the Christoffel symbols, and then 2 more lower indices in red which came from the 2-dimensional space under consideration x1 and x2. Shown here as uppers, but of course they are on the bottom, so they are lowers here. Just think of this R1, 1, 1, 2 as a number, what we previously called A. Then, using that same rule, we can also write the B, C and D coefficients like this. Then, with this new shorthand of using these R's with 4 indices, we can write the contravariant components dv1 and dv2 of the change in the vector v, as this is taken round this 2-dimensional loop dx1, dx2, as this. Now this might not look much better, but when we get to more dimensions, the numerical versatility of using indices will be helpful. We won't need constants a, b, c, d, e, f, g, h, i right through the alphabet. We can just use different numbers for the indices of r. So in 2 dimensions here, these 4 values a, b, c and d at the point which we're now writing like this could be said to be the components of some kind of tensor at this point in the space, and we will call it the Riemann Curvature Tensor. That tensor has 1 upper and 3 lower indices. The blue ones here come from the Christoffel symbols, and the 2 red ones come from the loop dimensions x1 and x2. We can write it more generally for space as R, R, S, M, N. Now, if you think about it, normally with a 4-index tensor like this, we would expect there to be 16 terms for 2-dimensional space. 2 times 2 times 2 times 2, and yet we only have 4 terms here in our equation. Why might that be? Well, it's because we've ignored some possible loops, or what we might call loops. We have fixed the rotation as dx1, dx2 in taking the vector around the loop. We're ignoring other possible loops for such a calculation, even while using the same directions x1 and x2. For example, what about the loops x1, x1, or x2, x2, or x2, x1? Well, okay, granted the first 2 of these extra ones are not really loops, they are backwards and forwards along the same line, and the third extra one is just x1, x2 in the opposite direction. When we come, however, in a moment to try to generalize this Riemann curvature tensor to 4-dimensional space-time, we will have to include all such possibilities. That's the nature of going over to a numerical way of organizing the old constants a, b, c and d. In other words, we will have to include all the numerical possibilities as entries in the tensor, And we'll have to live with the fact that some of them, such as going backwards and forwards along the same line to measure the curvature, seem to tell us nothing at all. And some of them relate somehow to producing the negative of others. Before we do that, let's look at our simple two-dimensional equations for dv1 and dv2 again, this time without the colouring of the indices. Notice that the first upper index of the Riemann tensor is the same as the index of the dv component which it is computing. 1 for these two because they're in the dv1 equation, and 2 for these two because they are in the dv2 equation. The next lower index is made to be the same as the component of v that it's multiplying. 1 for the first one in each bracket, which multiplies v1, and 2 for the second. Don't worry that the r index is lower, covariance, and the component index is upper, contravariant. The r index, if you remember, comes from the Christoffel symbol, but there is actually agreement between the two. Finally, we've already said that the last pair of the lower indices, 1 and 2 in this case, are common to all things in this particular situation. They are the same for each of these coefficients and represent the fact that the parallel transport took place around the infinitesimally small parallelogram dx1, dx2. This is obviously because at any particular point where we place this vector in this two-dimensional space, like this red dot, there's only the one tangent plane to think about, and so we can only take a pair of independent axes for the infinitesimally small parallelogram in order to parallel transport, and the obvious directions are those of the x1 and x2 axes. However, that will not be the case later when we have more than 2 dimensions. Think, for example, about a 3-dimensional space, not space-time just yet, simply a 3-dimensional space. Here's one which is bounded with a box for convenience, x1, x2 and x3. If we chose this point, this red dot, at which to measure the curvature of this space by taking a vector around a loop, then there would be 3 independent loops that we could take. We could, for example, use dx1, dx2, the plane through the point which is parallel to the front and back faces here. Or we could take dx1, dx3, the plane parallel to the top and bottom faces. Or we could obviously use dx2, dx3, the plane parallel to the 2 side faces in this simple diagram. Furthermore, as we are likely to be dealing with 4-dimensional space-time, there'll be a few more possibilities in addition to these 3. And if we want to investigate the curvature at one point, or rather event, in 4-dimensional space-time, we will actually have 6 two-dimensional planes of sorts that we can choose, and in a way the curvature is going to be much more complicated. In simple terms, there will be 6 independent ways in which to investigate the curvature at the point, or rather at the event, in the space-time, by using each one of those 6 independent planes. There will therefore be 6 independent loops that a vector could be taken around in order to detect a change in it at that event, and each of them would give us a different set of r values as measurements of the curvature. Using the axes defined by the coordinate system, these 6 planes would be dx0, dx1, dx0, dx2, dx0, dx3, dx1, dx2, dx1, dx3 and dx2, dx3. Here they are arranged in what will hopefully be shown in a moment to be a more meaningful way. We should of course add the other so-called loops to make the whole array mathematically complete, and so these are all the possible so-called loops for the 4-dimensional space-time written out in a 4x4 array, and these, the black ones, are what we might call the 6 useful planes. You can also see that these 4 diagonal ones might be thought in some ways to be less meaningful. They're not really loops being forwards and backwards along the same line. Also, these bottom 6 are in some ways duplicates of the top 6, just going around the loops in the opposite direction and therefore getting the negative of those values for the changes in the vector components. Nevertheless, you can probably see that mathematically this is quite a sensible way to organize things. It makes a neat and logical 4x4 array which will fit in well with our tensor mathematics. We'll have to include all of these 16 so-called loops from four-dimensional space-time in the mathematics, even though some of the entries seem to give duplicates of others and some don't involve taking a loop at all. But before we move on to looking at the results from all these loops, let me clarify one point. When we looked at the single plane x1, x2, the parallel transport of the vector v gave these two equations for the changes dv1 and dv2 in the components. Now, on account of the fact that we have four-dimensional space-time, it means that if we look at the curvature at a point by going around the rectangle in those same two dimensions, dx1, dx2, we would actually have four equations for the changes in the components of the vector. What we're doing is we are picking a point or event in four-dimensional space-time, but in looking at the curvature at that point, we are only for the moment going to consider taking the vector v to be parallel transported around a loop in the x1, x2 plane. And this would give us these four equations for the change in each of the four components of our vector v as we take it around that loop dx1, dx2. Let me repeat, this is four-dimensional space-time. So the vector is what we would call a four-vector and has four components. However, we are, for the moment, parallel transporting that vector v around a loop in only one of the planes, namely x1 and x2 of the space-time, and the vector v changes in all four of its components, so we get these changes in the vector dv0, dv1, dv2, and dv3. You can see that once again I've put the 1 and 2 indices from the x1, x2 plane in red. These are fixed for these particular four equations because of the plane we're considering. You should notice, of course, that even here we have 16 R coefficients or constants representing the curvature at that point or at that event. 16 numbers to describe the curvature of the space-time at that event. And that's just for parallel transporting around one of the 6 possible planes. As mentioned a moment ago, we could parallel transport the vector around a total of 6 different independent loops. Or rather, if we include everything, even what seem to be redundant loops, we could be considering not just these 6 within the mathematical equations, but a total of 16 possible so-called loops in this four-dimensional space-time, and this would make a total of 16 times 16 R-type constants, giving us 256 components altogether for the Riemann Curvature Tensor, and these come from 64 possible equations, some of which, of course, would seem to be redundant. Now, before we try to illustrate all of these, and it shouldn't be made simpler in a moment, as you'll see, here once more are the 4 equations for the changes in the contravariant components of a 4-vector v when it is parallel transported in the x1, x2 or xy plane around a point within four-dimensional space-time. The indices representing the x1, x2 plane or the xy plane have again been highlighted in red. We have here 16 R coefficients representing the curvature related to that event or point and to that loop from the x1, x2 plane. Now these 16 coefficients or R values could be put in an array and then in a box like this. Notice the 1, 2 in red at the top of the box. This is simply to stress that these 16 entries relate to coefficients needed to calculate the 4 contravariant components of dv when the vector is parallel transported around the dx1, dx2 loop at the point in the plane. This gives one particular aspect of the curvature at that point. Obviously, for the same point or event in space-time, the same red dot, we could transport the vector within a different plane, say the x1, x3 or xz plane. This would give a different resultant vector v' and hence different measurements of the components of dv0, dv1, dv2 and dv3 for the change in the vector v. The equations for dv0, dv1, dv2 and dv3 would look very similar, but the r coefficients would have different values and be labelled with different indices. Here is the array for the x1, x3 plane. Notice that the only difference in the labelling compared to the first box is that these all have 1, 3 instead of 1, 2 in all the components, but of course the 16 numbers that these r's represent would be entirely different. We could also include, of course, the r values for the 0, 1 plane, the plane which is made up of light in one direction and the x-axis in the other. Again, notice that the labelling of the r's is appropriate. Let's add a few more. These are, in a sense, all of the meaningful ones, the sensible ones, from the 6 planes that one can easily imagine within 4 dimensions. These might be said to be the negative versions of those, obtained by parallel transporting the vector v in the opposite direction, 1, 0 instead of 0, 1, and so on. Now, in order to include mathematically all the possible indices, we must also add this diagonal set of coefficients. It's conceivable that they might not all be 0, but certainly the equations that they form part of will produce 0 for the changes in the vector. After all, the vector v will not have been transported around any meaningful loop, but simply gone backwards and forwards. So this whole array of numbers, each of which has been suitably labelled with appropriate indices, is what we can call the Riemann Curvature Tensor, and it's given the symbol r, rho, sigma, mu, nu. Greek letters when we're talking about space-time, don't forget. As it has 4 indices, it means that when applied to 4-dimensional space-time, this Riemann tensor will have 256 entries in the matrix, 4 times 4 times 4 times 4. A good number of these may not seem to convey any meaningful information, but they are all indeed needed for mathematical completeness. This Riemann curvature tensor has 1 upper or contravariant index and 3 lower or covariant indices, and you should be able to see why this should be so from the way in which it came about via calculating the change in a vector after parallel transportation in a loop through the metric tensor and the Christoffel symbols. We gave the formula for calculating these components earlier, but certainly didn't prove it, and here it is again. Each of these 256 entries in the Riemann curvature tensor could be calculated from this formula, which relates them to the Christoffel symbols. And you should remember once again that in 4 dimensions this will be 4 terms, as will this, because of the sums over lambda. To illustrate the complexity shrouded in simplicity, one might say, here is how one might go about calculating just one of these 256 coefficients. Let's say r, 0, 1, 2, 3. First put in 0, 1, 2, 3 for rho, sigma, mu and nu, leaving lowercase lambda to be summed over. Then do the sums over lambda for 0, 1, 2 and 3, and that gives us these terms altogether. Now take the formula for the Christoffel symbol, work out what each of these is by putting in the appropriate indices, and put those into the equation for r, 0, 1, 2, 3. Do the differentiation where needed, substitute for the known values of the metric tensor at the point or event, and for its various derivatives and second derivatives, and you will end up with a number for r, 0, 1, 2, 3, a simple scalar number, just one of the 256 entries in the Riemann curvature tensor. Now, whilst the Riemann curvature tensor is the most complete way to describe the curvature at a particular point in a particular metric, even to the casual observer, there does seem to be a good deal of redundancy in it. If you hadn't realized it already, the summation convention can hide a multitude of complications and give that shroud of simplicity. All that complicated type of calculation is embodied in this formula for the Riemann tensor, and it represents all 256 entries in four-dimensional spacetime. The same, of course, applies to the various formula for the components of the change in the vector with which we started this discussion. These can all be written using the summation convention and can look deceptively simple. You should recall that from this expression, if you consider a particular loop dx mu dx nu in four-dimensional spacetime, in other words, two actual values of mu and nu, this will give you four equations, rho here going from 0 to 3. Each of these equations will have four terms, sigma running from 0 to 3. In principle, there are 16 independent loops for mu nu that you could choose, and so 16 lots of the 4dv components, although in practice there are only really 6 independent two-dimensional planes within which to make those loops. Anyway, whilst this Riemann curvature tensor kind of makes sense and is very comprehensive even to the point of seeming to contain redundancy, it doesn't seem as though it will be much help directly in producing Einstein's field equations. Why do I say that? Well, everything about space-time geometry so far has been about tensors with two indices. In particular, of course, the metric tensor, which we know will be pivotal, is written as g mu nu, and must surely feature in those equations. We would probably expect Einstein's field equations to be tensor equations with two indices throughout. And in fact, jumping ahead, we know that Einstein eventually formulated equations of exactly that form. Here is the metric tensor, multiplied only here by scalars. And so every other term in this equation, or equations, must agree with that, in the sense that they must also have two indices, mu and nu, and of course they do. This, for example, is known as the Ricci tensor, and looks as though it fits the bill in this equation, in that it has the same type of lower indices as the metric tensor. But what is it? How is it calculated? And what does it mean? Well, in one sense, it's fairly easy to explain how the Ricci tensor is created, what it is. It's not so easy, in fact, it's quite mathematically arduous to explain what it does. But let's go for the easy bit and make some sweeping statements along the way in order to get us through it. We now know that the Riemann curvature tensor, even though the mathematics is complex, is fairly easy to comprehend at this level. It has to do with parallel transport of a vector around infinitesimally small loops and gives some kind of measures, in fact lots of measures, of the curvature at the point when the loop area tends to 0. The curvature at any point can be represented by the 256 components of the Riemann curvature tensor in four-dimensional spacetime. And you would need to know all the facts about the metric tensor at the point in order to evaluate this whole thing. The simple fact about the Ricci tensor is that it can be said to contain a subset of the components of the Riemann curvature tensor. In other words, you take some of the 256 Riemann tensor components, combine them in groups, and throw the others away, and you end up with the Ricci tensor. It still measures curvature, but does not contain as much information as the Riemann tensor. That process of choosing parts of the Riemann tensor to create the Ricci tensor is via the process known as contraction. Now, we've not really talked much about the concept of contraction, so here's a simple illustration of it. Suppose you had a tensor such as this, T mu nu lambda. In four-dimensional space-time, the fact that we have three indices means that this tensor would contain 4 times 4 times 4, 64 components in four-dimensional space-time, every event in space-time would require 64 numbers, scalars, to describe that point. There are different ways of trying to display this. Here's one, for example, not necessarily the best, but it will help me in a moment to show something else. There are four 4x4 arrays here, each similar looking to one another, but with, in this case, different upper indices, and we can show these in red: 0, 1, 2, and 3. The main thing to realise, of course, is that although it could be displayed differently to this, it is saying, amongst other things, that we have 64 different values or components of this tensor at each point or at each event in space-time, and these different values are addressable using the indices. A tensor with 3 indices in 4 dimensions means that we must have 64 components, which means 64 values at each event. However, if we wanted to take a subset of those 64 terms and throw the others away, we could imagine getting a much simpler looking tensor, and it might still be useful. We could do this in lots of ways, depending on what we wanted to get rid of or what we wanted to keep. For example, by contraction, we could first set 2 of the indices, an upper and a lower, to be the same letter. Let's make, say, mu and lambda here both equal to mu. We would then, here, have an implied sum over mu. And doing this sum would give us 4 terms in 4-dimensional space-time, each of which would be the sum of 4 things. Note that this new tensor with only one lower index is in fact a vector, but I'll give it the letter t so that each of the components of this new tensor's vector is made of 4 terms, like this, where nu runs from 0 to 3. In other words, these are the 4 components of the new vector in 4-dimensional space-time. It's not the same as the old tensor because it only has one index, nu in this case. It's a vector. This equation represents the 4 covariant lower components of the vector t. Each of these components of the vector contain 4 of the original rank 3 tensor components. So to flesh this out, we could write the new vector like this. Pictorially, you can see that the way this new vector is made up from the old tensor is by taking particular elements from it, namely from the first, second, third and fourth columns of the old tensor. For example, T0 is the addition of these numbers on the top row. The other 3 components of the new vector are made up in a similar fashion. Now that's a simple example of this kind of use of contraction. You more or less pick a subset of the components of the old tensor to make a new, simpler tensor. In this particular example, it was a tensor with 64 components, and it became a vector, a rank 1 tensor, with only 4 components. And that's the kind of process we want to use in order to get to a new tensor, the Ricci tensor, from the more complex Riemann tensor. The Riemann tensor has too many indices for us to use in what is likely to be our field equations, and in any case it seems to contain a lot of redundancy, components that seem to do nothing and could perhaps be thrown away. We need to reduce the number of indices to 2 in order to make a simpler tensor which hopefully will be able to be used in a field equation. This reduction in the number of indices can be done by contraction. In this case, the contraction of rho, the upper index, with any of the 3 lower indices. I say any, but in fact doing it with sigma doesn't produce anything useful, and doing it with nu just produces the opposite of doing it with mu. So let's take mu. In other words, we first set rho, the upper index, to be the same as mu, the third of the indices, and I'll call them both rho. That then implies that this expression must be summed over the index rho, and when that sum or contraction is done, it gives a 2-index tensor called the Ricci tensor, which we'll call r sigma nu. Each term in it is the sum of 4 of the Riemann terms. In four-dimensional space-time, this Ricci tensor R sigma nu is clearly a 4x4 tensor, a bit like the metric tensor. And each of these entries is made from adding together four of the components from the Riemann tensor. Here's an illustration of that for four-dimensional space-time. To calculate each of the 16 terms, you would simply put sigma and nu each equal to 0, 1, 2, and 3 in every combination. If you want to see more clearly how it relates to the Riemann curvature tensor, then perhaps a better way, at least at this stage, to see what's what, is first of all to look at what we understood, or at least I hope we understood, to be the Riemann curvature tensor, all 256 components within it. The rows in which the first and third indices are equal are these. These are the rows which will contribute to the contraction to produce the Ricci tensor. This first row, for example, contains Riemann tensor components with 0 in both the first and third index places. This is the only row for which that's true. This row, on the other hand, is the only row which has components with 1 in both the first and third index places. This one has 2, and this one 3. These are the special rows. And if we now add up all the entries from those rows that are in the first column, it will give the Ricci component R0, 0. The reason being that all these terms have 0 in both the second and fourth index of Riemann, so we have 0 in both of the Ricci indices. Adding those selected Riemann terms from this second column together produces the Ricci component R1, 0, and from the next R2, 0, and then R3, 0, and so on. Hence we get these 16 components along the bottom here, which are the 16 components of the Ricci tensor. If you think about it, these 16 components have been made up out of 64 terms from within the 256 terms of the Riemann curvature tensor, and are here arranged into 16 components in a 4x4 matrix. If we were to write down these 16 components of the Ricci tensor in terms of the subset of the 256 Riemann components, they would look like this, where the Ricci indices have been highlighted in red. So that's what the Ricci tensor is. But why would you want it to be that? What does it do? Why is it there? We know that it will play an important part in the Einstein field equations because we know that's where we're heading. But why? Well, most of those questions can only satisfactorily be answered through some rather intense mathematics. However, when we come later to the simplistic derivation of Einstein's field equations, things should be a little clearer, and hopefully there won't be the need to ask those questions. For now, it's possibly worth mentioning, without going into the mathematics, that the Ricci tensor can be considered to be involved in the way in which certain entities can be measured to change their volume as they travel along geodesics. This is usually explained in terms of a cloud of powder or dust particles, each of which can travel independently from one another. Suppose for simplicity we had 4 such particles at these red dots in this two-dimensional space at some particular time. Now granted, we don't have time in this diagram, we only have 2 physical dimensions, say x1 and x2, but just accept that the positions of the particles as shown here are simultaneous events as perceived by all slowly moving objects. They are in these positions at a particular time. We'll also suppose that all of these particles have velocities in this two-dimensional space and are travelling along their geodesics. They are what we might call free-falling, but the space and the metric measuring them is curved. As far as the particles themselves are concerned, they are each travelling in straight lines within the space, but someone measuring their position using the curved metric would suggest otherwise. For example, in this situation, given that we can see here with our extra perspective on the situation, we can say that at later times these particles will be measured to be closer together. Now don't forget, we can't talk about there being a force between the particles, and yet there appears from our measurements to be such a force as they free fall along their own geodesic. For example, suppose we started with, say, a cloud of minute powder or dust particles in this region here. The dimensions of the cloud could be measured as shown. Assuming also that the particles are free falling, that they don't interact or bump into one another, then by the time they get to this region, the dimensions of the cloud will be measured to have shrunk. Of course, if the curvature of the space were different, then it may be that the cloud would be measured to be bigger. The Ricci tensor can be used to describe this kind of effect. Now, don't get me wrong, this doesn't mean that the volume of some solid object will shrink or grow as it moves on its geodesic, but internal forces trying to stretch or shrink the object will come into play. Any change in volume as shown in diagrams here really relates to what we might call a co-moving or non-interacting particles. As each particle moves along its geodesic, the distance measured between the particles will change in accordance with the Ricci tensor. And of course the Ricci tensor is just bits and bobs of the metric tensor, so it's the metric tensor that's doing these measurement changes. As mentioned earlier, it's not easy to show this mathematically, but just as well, we will not need this idea when we come to use the Ricci tensor in Einstein's field equations. We simply need to know what the Ricci tensor is. It is a rank 2 tensor made up of some of the components of the Riemann Curvature Tensor, and it contains in its 16 components enough information about the curvature at a point in space-time that it can be used in those field equations of Einstein when we get to them. The third measure of curvature that we need to consider is the Curvature Scalar, or as it's sometimes called, the Ricci Scalar. It's derived from the Ricci tensor by essentially throwing away some terms, summing others, and coming up with a single number, a scalar, a single number at each point in space. It is simply represented by the letter R. Being a rank 0 tensor, i.e. a scalar, it obviously has no indices and has a single value, as I say, at every point or event in space-time, a single but probably different value everywhere. Before we get into what the curvature scalar is, one might well ask what use is a single number likely to be for a point in space or space-time, even if it does embody something of the curvature at that point. If the previous argument for the Ricci tensor was bolstered by the fact that we think we will need an equation where each of the terms must be a rank 2 tensor, i.e. have 2 indices, why would we suggest that a single number, a scalar, might also be useful? Well, as was mentioned earlier, when we come to a simplified derivation of Einstein's field equations, such questions may be easier to ignore. At the very least, at this stage, you can see that looking forward to the Einstein equations, that the presence of this curvature scalar is in multiplying the metric tensor, and so the whole term here is still a rank 2 tensor, the curvature scalar simply being a multiplying number. Okay, so what is the curvature scalar, and how is it taken from the Ricci tensor? Here's the Ricci tensor once again for 4-dimensional space-time. Well, the curvature scalar is essentially the trace of the Ricci scalar, but not quite. If you've done a little on matrices, you'll know that the trace of the Ricci tensor would be the sum of the diagonal elements, and so would be equal to R00 plus R11 plus R22 plus R33. However, written like this sum could not be expressed using the contraction shorthand and summation convention, because for that type of addition, one index must be contravariant and the other covariant, one upper and one lower. In other words, we couldn't really change this R sigma nu into this R nu nu, and then make some kind of implied sum of the diagonal elements like this. It's not allowed mathematically. However, there is a way to do it. As was mentioned earlier, an index of a tensor can be raised or lowered using a form of the metric tensor. So that, for example, if we first raise the first index of the Ricci tensor like this, and then once we have a tensor with one upper and one lower index, r sigma nu, we can then make the two indices of this new tensor equal to, say, nu, and then do the implied sum. This is the curvature scalar, and so we simply give it the letter r. If you think about how it was created all the way back to the Riemann Curvature Tensor, this deceptively simple-looking single number r, a scalar, at each event, has a lot of information folded into it. Each of the four parts of it shown here is made up of a number of the components of the Riemann tensor. And just as we gave a simple illustration of the Ricci tensor as being to do with the way in which a cloud of dust particles would change its overall volume as each particle travelled along its geodesic, so we can give a simplified meaning to the curvature scalar. In many ways, its value at some point or event can be thought of as a measure of the average spatial curvature at that point. It may well vary with time, but in simple terms, it can be thought of as a single measure of the curvature of the space at that point and at that time. If it's positive, then the four-dimensional space-time surface, if you can get your head around that kind of language, the four-dimensional space-time surface at that point could be said to look like a sphere or ellipsoid, and the volume of a small sphere there would be smaller than one of the same radius in Euclidean space. However, if the curvature scalar is negative, then the four-dimensional space-time surface is more like a saddle shape or hyperboloid at that point, and the volume of a small sphere is greater than in Euclidean space. For r equal to 0, of course, the space-time surface is flat at that point. And as we'll see when we come to our simple derivation of Einstein's field equations, the curvature scalar will be an extremely important multiplier in those equations, whose presence will be crucial in ensuring a correct form of those equations. However, before we get to that, we have one more thing to sort out, which will be covered in the next video. If you look at Einstein's field equations again, you should notice that there is one thing that we haven't yet discussed. This, the stress-energy-momentum tensor. And we will begin to explore this after thinking a little bit about four vectors. And once we've got the stress-energy-momentum tensor under our belt, we can then try to put all the pieces together to create and have at least some understanding of the Einstein field equations. Having discussed the Ricci tensor and the curvature scalar in this video number 17, in the next video number 18 we'll discuss something else that we'll need for the Einstein field equations, namely the stress-energy-momentum tensor.